This is Matt. I just completed my fourth week of supply chain engineering at Georgia Tech, a 1 year's master's course, and I wanted to do a little bit of review of our one of our courses that did probability for supply chain. I just felt like the notes were kind of all over the place. So for my own kind of review to get better and to have a better understanding of it, and then for anyone else who wanted to learn about probability and supply chain, it's mostly just simple statistics, but a couple of the later slides or questions are more directed towards supply chain. So to start off things, we're just going to go over basic terminology. So an experiment is any procedure that can be infinitely repeated with an unknown outcome. So the typical example is flipping a coin, but for this, I'm going to using rolling a six-sided die uh, for the rest of these examples. Then the outcome is the result of the conducted experiment. An example is a 1, but then you could also have every other example of a six-sided die. Then the sample space is a set of all the possible outcomes. So for our six-sided die, it would be 1, 2, 3, 4, 5, and 6. Or if it was a coin, it would be a heads or a tails. An event is a subset of the sample space. So the subset could be, for instance, all the even numbers. Then the probability is the likelihood of that event happening. For this example, it would be 50% of our even die roll. So moving on to conditional probability is probability of A given B. So given an even number, what are the odds that that number is 4? So because an even number was 50% of the total outcomes, and then a 4 is a sixth of the total outcomes, that would be about 33%. I should fix that colon. Definitely out of place. Okay, so moving on to mutually exclusive. So the union of A and B is 0. So a typical, or so back to the coin example, you can't get a heads and a tails. So for our die example, given an even number, odds of rolling a 1. So you can't have an even number and a 1. Then the law of total probability is always adds up to 1. So all your possible outcomes have to add up to 1. Otherwise, you're either missing an outcome, or you've counted the probability somehow wrong, and something is more probable than you accounted for. So for our example, because there are 6 sides of the die, everything has a 1/6 of probability of happening. So independence, the probability of A and probability of B, they do not affect each other. So if I get a 1 on the first die roll, that doesn't make the 1 less likely or more likely to happen on the second die roll. So, for instance, 2 independent events would be rolling the die twice, flipping the coin twice, and so on. So the next major thing that we covered in the course so far is Bayes' rules. Bayes' rule describes the probability of an event based on prior knowledge of related events. Typical examples of this are used in healthcare or car insurance. So for car insurance, since people under 25 are more likely to cause an accident, they assume that drivers under 25 will crash more often. So therefore, they're going to charge someone under the age of 25 a higher fee than they do of someone over the age of 25. Or if you have a history of having a car accident, then then they will charge you more for your car insurance. Similar for health insurance reasons. If you have a history of being sick, or a history of having a higher fee, chances are higher that they will charge you a higher fee. For this instance, here's the simple math of how the Bayes rule shakes out. So you have to have on the bottom, in the denominator, you have to account for all possible cases. So P positive given a user or non-user. So a user is 5%, a non-user is 95%, and then positive given user is 90%, positive given non-user is 45%, is 20%. But so, and then the numerator is what you're trying to account for. So user given positive, so you have the positive given user times the user, so 90% times the 5% to get 19% as the estimated probability that it's a user given that it's a positive result. So you're essentially reversing the expected outcome, where you can swap what was assumed from what was known based off prior knowledge and this estimation of Bayes probability. And it can be compounded, such as for our example that we did in class of different COVID tests. So if you test positive once, that increases the likelihood that the positivity is in the future, or if you test negative, it makes it less likely that you get multiple negatives and still be actually positive. So moving on to discrete random variables. A random variable is mapping from a sample space. So in our example, number of even numbers when you roll a die twice. So that could be 0, 1, or 2. But a discrete random variable is, it can either, there is only an instance of like 0, 1, 2, or 3. Like there are no like in between numbers that can appear. So the probability for P of x is always between 0 and 1 for any random x, but the sum of all the probabilities, as always with probability, adds up to 1. The probability between A and B is equal to the sum of the probabilities between A and B. On our right, we see a CDF, and because it is a discrete random variable at each instance, there is a probability. The cumulative distribution jumps up. So we go over, we jump up, we go over, we jump up, we go over, we jump up. A question that could be asked, given our background in supply chain engineering and the focus of this course, is what is the probability of the demand being at least 5? So that means what is the probability that demand is greater than or equal to 5? So it's just kind of a rearranging of the terms. Or another question that we could be asked is, what is the probability that we experience a shortage? So experiencing a shortage means there isn't enough supply in stock to treat the random demand. So that means the probability, assuming that the supply we were given was 10, what is the probability that the demand is greater than 10? So then the next probability that we were faced throughout the beginning of this course and the beginning of the homeworks is probability that we can't fulfill demand. We want to be less than 10%. So we want probability of x greater than gamma, gamma being the probability that we can't, or the demand that we can't fulfill to be less than 1. So the probability being greater than gamma being less than 1. So it's kind of choosing where we want our supply to be so that the demand or the probability being greater than that amount is less than 10%. So that moving on to from discrete to continuous, rather than being an individual number, it can be described as a summation. Now we're going to be describing variables more of as an integral. So the integral of the variable is equal to 1. The probability of x equal to a variable is always 0 because you're looking at like a tiny segment, and that's just a definition of continuous. The probability that x is between a and b is the integral of fx dx from a to b. The big F of x is the integral of the function from negative infinity to x. P quartile is the probability that x is less than gamma, less than or equal to gamma equals p. The definition of a PDF is the probability distribution function. So between x is less than 0, for our example, is 0. The between 0 and 30, the distribution is 1 over 30, and then the distribution over 30 is 0. So I guess moving back to f of x, the probability at any point is always greater than 0, but it is not defined by 1. What that means is there could be a like sample space where the probability is in between 0 and 0.1, and in between that the probability is 10. So, but that is because the total area adds up to 1. So moving back to the bottom of the page, the cumulative distribution function is 0 when x is less than 0, x over 30, when 0 is between x, or when x is between 0 and 30, and then 1 when x is greater than 30. So it's essentially the integral of the PDF. So continuing with continuous random variable, looking at the probability of being late, given that the definition of late is 2, the probability of being late is the probability that x is greater than 2. Another common question, order delivered being on time with a probability of 0.9. You want p delivered on time to equal 90%, and you're trying to select a time to say so that you're 90% on time. This can be, so you're selecting a gamma so that p of x less than gamma equals 90%. Then the probability of stock out being with x being 15, or the stock being 15, or the probability of stock out that you want to be out of stock less than 10%. So PR of stock out equals PR of x greater than 15, which is 1 minus the probability of x less than or equal to 15. So moving on to PR of stock out of 0.1. So that's PR of x, which is greater than or equal to gamma, which is your stock. That would be the answer to this question, or that the answer that they're looking for. So gamma being PR of x greater than or equal to gamma less than 0.1, or 1 minus the probability of x less than gamma is less than 0.1. Mean expected variable, or expected value. So the sum, to get the mean, you multiply the probability of each value times the value to get the mean. So if you have a probability of 20% at 0, 50% at 5, and 30% at 10, 20 times 0 plus 50 times 5, or 0.5 times 5 plus 0.3 times 10, and that would be your mean. Continuous is just an integral instead of a sum. Variance is the standard deviation squared, but also the distance that each value is from the mean. Shortage, we've kind of gone over shortage, but shortage only appears when x is greater than the given storage. So q in this function would be the given storage, and x minus q, when x is greater than q, is the given shortage. So expected tardiness. Tardiness is kind of similar to shortage, but in the time domain rather than the domain of items. So given that, like, what is the expected shortage? Given that x is greater than 2, what is the expected delay? 95% delivered on time. This is, again, kind of similar to the probability of being out, not having stock out. So probability of 90 delivered on time equals 95%. PR of x less than or equal to gamma equals 95, or 1 minus PR of x greater than gamma equals, or is less than 5%. So moving on to dependent. Not everything is always independent. It's hard to make that assumption, but you essentially have to do the distance that the x and the distance that the y is from the x mean and the y mean, and then to normalize it, you divide by n minus 1. But the issue with that is if we're in different units, that makes things chaotic. Of what is, if the distribution is in thousands of dollars, what is the distribution in pounds? What if the distribution is in cents? Like, it's hard to come to terms with that and have a good understanding of the relationship. So to find the unit free, we divide the covariance by the standard deviation of x and y to get a unit free correlation. So normal random variable and central limit theorem. The mean, it is mu, and variance is variance is the standard deviation squared. Oftentimes we're going to refer to the z-score, which is z-score, the z equals x minus mu, the mean, over the standard deviation. And chances are we're going to have normal standard tables in which you're going to look up a number, compare that for a normal distribution, which we can see in the bottom, which the center is located at the mean, and then 34% is between the mean and the first z-score. The second I think is 95%, but or very close to 95%. And then the third is like 99.7, and that's within 3 z scores on either side, so the total distance of 6 z scores. Then the central limit theorem. The central limit theorem basically states that if you have a sample that is larger than 30, the mean and the standard distribution begin to resemble the sample population. So if you have, essentially your sample size has to be larger than 30 to begin to resemble the total population. So I guess that could be used in polls, that could be used in for candidates, that could be used for any given sample that you're looking at a distribution, whether that is, I guess, COVID cases, if you're looking for positivity, negativity. But as usual, the more samples you get, the closer you will to resembling the typical sample. Moving on to other stuff from last week. Sorry, this is kind of 2 days late. The weekend was kind of hectic, and then when we had 3 homework assignments, and then this also took a little bit longer to prepare than I was expecting. Just with all the math formulas, it takes a little bit more time to write each formula. But supply chain engineering and warehouse distribution, we had a class interview for ecom spaces, which was the classes essentially split into 2 projects with 5 teams on ecom space and 6 teams on the other project. My project is ecom spaces, and we're looking at how we can help this distribution center better set up their facility as they grow into the future. They're currently in kind of a startup stage and remodeling to better be prepared for the future. In Operations Research 1, we were looking at the duality problem and how that is resembled and related to the primary problem. Operational Research 1, we were looking at the case 1 problem, which we have an approximation due today, and then the full case is due next Tuesday, and that is more of looking at a scenario in which we have to plan for 10 random events, with some that can't start till another random event is complete. In this scenario, we're preparing for a music concert. So, for example, you can't advertise who you booked for the concert till you booked them. So there are different dependencies, right, based on that. That you could also use the example of building a house. You can't put it on a roof till you put up the walls of the house. In entrepreneurial finance and private equity, we looked at different VC deals. And then job recruitment, I applied to KPMG and Ernst Young. Thanks for listening. I feel like this is longer. Ew, 24 minutes. We'll see. Thanks for listening. Bye.